I will speak about continuous groups of binary transformations. But first about motivation. Why is it an important and natural to consider and to investigate continuous invertible binary operations of topological space? Let X be a topological space, and let C of X be the set of all continuous maps from X to X. Or in algebraic terminology, the set of all continuous unary operations of X. This set is a topological space endowed with a compact open topology. Moreover, this set is a topological monoid under the composition of two maps as a monoid operation and with the identity element as the identity map of a topological space X. So we have a monoid. Therefore, we can consider the set of all invertible elements of this monoid. Let's denote this set by H of X. It is easy to see that H of X is a group. However, it is not a topological group. But it is well known that for good spaces, Hx is a topological group. For example, when X is metrizable or when X is compact, then Hx is a topological group. Note that the group H of X and all its subgroups naturally act on X. Moreover, any topological group which acts on X effectively is isomorphic to some topological subgroup of the group H of X. Therefore, we can say that the group H of X, or again, in algebraic terminology, the group of all continuous invertible unary operations of X is a source of groups acting on X. But in all these argumentations, one can consider binary operations instead of unary operations. And in this way, in my paper published in Mathematical Notes in 2014, the notions of a binary action and a binary G-space were introduced. Next in my talk, I will construct the group of all continuous invertible binary operations and define the notions of a binary action and a binary G-space. And then I will present some results of the theory of binary G-spaces, which can be found in the following papers. I will show this slide again at the end of my talk, so let's continue. Let X be a topological space. Denote by C sub 2 of X the set of all continuous maps from X squared to X, or which is the same, the set of all continuous binary operations of a topological space X. Again, this set is a topological space with a compact open topology. But the main question which arises here is how to define the composition or multiplication of two binary operations of a topological space X. There are different ways to do this, but we will define this composition, this multiplication by Formula 1. And one can note, one can prove that the set C sub 2 of X with multiplication 1 is a topological monoid with the identity element as a second projection. Again, because we have a monoid, we can consider the set of all invertible elements of this monoid. Let's denote this set by H sub 2 of X. But it is important to know which binary operations of a topological space X are invertible. And this theorem provides an answer to this question. A continuous binary operation f from x squared to x is invertible if and only if, for any a in x, the map f sub a from x to x defined by this formula is a homeomorphism. And using this theorem, we can prove an important result, that a continuous binary operation f from x squared to x is invertible if and only if it is a continuous left quasi-group operation on x. So, according to this, to previous assertion, we can say that h sub 2 of x is the group of all continuous left quasi-group operations on x. This group, in general, not a topological group, but when x is a locally compact and locally connected space, then h sub 2 of x is a topological group. Note that this group, h sub 2 of x, is a natural extension or generalization of the group of all autohomeomorphisms of x. Also in the sense that the group H of x is isomorphic algebraically and topologically to some subgroup of the group H sub 2 of x. So for any topological space x, we have constructed the group of all continuous left quasi-group operations on x, and whose elements act on pairs of points of x, or as we say, binary act on x. And this leads to the notions of a binary action and a binary G space. Let's define these notions. A continuous map alpha from G cross x squared to x is called a binary action of a topological group G on x if the following conditions hold. And the space x together with a binary action alpha, or the triple Gx alpha, is called binary G space. Okay, to establish a relationship between a group G and the group of all continuous left quasi-group operations of x, let us define a continuous map alpha sub G from x squared to x by formula 3. And it can be proven that the map G to alpha G defines a continuous homomorphism from the group G to the group H sub 2 of x. And the kernel of this homomorphism is called the kernel of the binary action. And the binary action is called effective if its kernel is trivial. And one can prove that if a group G binary acts on x effectively, then G is a subgroup of H sub 2 of x up to isomorphism. Therefore, we can say that the group H sub 2 of x, or the group of all continuous left quasi-group operations on x, is the source of groups which binary act on x. Let's give two examples. Let H be a subgroup of a topological group G. A continuous map alpha from H cross to G squared to G, given by formula 4, is a binary action of H on G. It is not difficult to verify this assertion. Particularly, any topological group G binary acts on itself by the same formula, which we say the binary action by conjugate left translation. And the second example, let's consider the general linear group of order n and vector space Rn. And let's define a continuous map alpha from this group cross Rn squared to Rn by formula 5. And it is not difficult to prove that alpha is a binary action of the general linear group on the vector space Rn. Now we need to define morphisms between binary G spaces. Let X and Y be binary G spaces with binary actions alpha and beta, respectively. And then a continuous map F from X to Y is called bi-equivariant if the following condition holds. You see, the family of all binary G spaces and bi-equivariant maps form a category which we denote by G top 2. To compare the category of all G spaces and the category of all binary G spaces, we need to induce to define some induced actions. Let X be a binary G space. Then we can define the map alpha sub X from G cross X to X for any X in X by this formula. And it is easy to prove that alpha sub X is an ordinary action of a group G on X. So one binary action alpha of G on X generates a continuous family of actions alpha sub X of a group G on X. Now let X be a G space. We can define a binary action of a group G on X by this rule. This binary action we call a constant binary action. So every topological space G, every topological space X, we can consider as a G space with the trivial action of a group G on X. And every G space X we can consider as a binary G space with the constant binary action of a group G on X. So the following category inclusions hold. Although the category of all binary G spaces is a natural extension or generalization of the category of all G spaces, the significant problems arise when we try to extend some notions and results from theory of G spaces to the theory of binary G spaces. And the first problems arise when we consider bi-invariant subsets of a binary G space. Let A be a subset of binary G space X. Denote by GA the set of all elements of X of this type, G of A1, A2. If G be a compact group and X be a binary G space, then GA is closed or compact when A is closed or compact, respectively. Now, a subset A is called bi-invariant if the set GA coincides with the set A. It is well known that in G spaces, the intersection and the union of two invariant subsets is also invariant. But this assertion is false for binary G spaces. More precisely, the intersection of two bi-invariant subsets of a binary G space is also bi-invariant. However, the union of two bi-invariant subsets is not generally bi-invariant. For example, each one-point set in vector space Rn on which the general linear group binary acts is bi-invariant. However, the union of 2 points or 2-point sets are not bi-invariant because of this equality. Therefore, the natural question arises, for which binary G spaces is the union of 2 bi-invariant subsets also bi-invariant? I don't know an adequate answer to this question up to this time. Significant problems arise also when we consider a notion of orbit and orbit space of binary G spaces. The minimal bi-invariant subset A tilde containing the subset A is called the saturation of A. And the saturation of the point X is called the orbit of X and denoted by X in square brackets. It is evident that the set G of XX is a subset of the orbit of X. However, in general, this set doesn't coincide with the orbit of X. To describe and to classify the orbits of arbitrary binary G space, let us define the set G to the n of X recursively in this way. Now, it can be noted that for any binary G space X, the orbit of a point X is the union of all these sets, G to the I of X. And the orbit of a point X is called n-generated if it coincides with G to the n of X, but doesn't coincide with G to the n minus 1 X. Otherwise, the orbit is said to be infinitely generated. The following two results are true. For any natural n, there exists a binary G space which has an n-generated orbit. And there exists a binary G space which has an infinitely generated orbit. To prove these theorems, we give suitable examples for each n. Unlike G spaces, in binary G spaces, orbits can intersect. And therefore, for any binary G spaces, we cannot define the notion of orbit space because orbits are intersect. But there is a large class or wide class of binary G spaces for which we can do it, for which we can define the notion of orbit space. Let's define these spaces. A binary G space X is called distributive if the following distributive law holds. Two examples. The binary action of the topological group G on itself by conjugate left translation is distributive. But the binary action by this formula doesn't have this property. And the binary action group on the vector space Rn is not distributive. Now let's define the notion of distributive subgroup. A subgroup D of H sub 2 f of X is called distributive if its natural binary action on X is distributive. Now let's formulate the important theorem on the binary distributive representation of topological group. Every topological group G is isomorphic algebraically and topologically to some distributive subgroup of the group of all left quasi-group operations of some topological space. This theorem is a binary topological analog of the classical Cayley's theorem on the representation of a arbitrary finite group by invertible unary operations, which is the same by permutations. As we mentioned above, the set G of XX is not generally bi-invariant, not equivalent, is not generally bi-invariant. And unlike G spaces, in binary G spaces, orbits are generally not disjoint. But in the class of all distributive binary G spaces, everything looks similar to the case of G spaces. More precisely, let X be a distributive binary G space, then the set G of XX is a bi-invariant set. And therefore, the orbit of X coincides with this set. And any two orbits in distributive binary G spaces either disjoint or equal. We can say here that in distributive binary G spaces, every orbit is one generated because G of XX coincide with the orbit, is bi-invariant. Thus, any distributive binary G space X is partitioned into disjoint classes of subsets, into the orbits of points. And let Xg denote the set of orbits, and let pi from X to Xg is an orbit projection. A quotient set Xg endowed with the quotient topology is called the orbit space of a distributive binary G space X. So for distributive binary G spaces, all is okay. Now let's formulate two results about orbit space of distributive binary G spaces. Let G be a compact topological group, and let X be a Hausdorff distributive binary G space. Then the orbit space Xg is also Hausdorff, and orbit projection pi is closed and proper map. And let G be a compact topological group, and let X be a distributive binary G space. Then the orbit space Xg is compact or locally compact if and only if X is compact or locally compact respectively. It is well known that the transitive G spaces play an important role, a key role for the classification of G spaces. Now our purpose to define the notion of transitive binary G spaces and classify them. A binary action of a group G on a subspace, on a space X, okay, on a space X is called transitive if the set G of XX coincide with X. In this case, X is called a transitive binary G space. In other words, we can say that a binary G space X is called transitive if it has only one orbit. The following proposition provides examples of transitive binary G spaces. Let H be a closed normal subgroup of a topological group G. Then the map alpha from G cross GH squared to GH, defined by formula 8, is a distributive and transitive binary action of G on GH. The following theorem shows that in the class of all distributive binary G spaces, there are no other transitive binary G spaces except previous GH. More exactly, let G be a compact topological group, then for any distributive and transitive binary G space X, there exists a closed normal subgroup H of G such that X is bi-equivalently homomorphic to GH with the binary action of G by conjugate left translation. And the second theorem shows that when we consider distributive and effective binary G spaces, then in this class, there is only one transitive binary G space. It is a group G by binary action on itself by conjugate left translation. More precisely, let G be a compact topological group and let X be an effective distributive and transitive binary G space. Then X is bi-equivalently homomorphic to the group G. This results about transitive binary G spaces have not published yet, and at the end of my talk, promised slide of references. That's all. Thank you.